Alright, so this is the ME113 project for fluid dynamics. Today we will be investigating buoyancy of an object that is sitting in two different fluids with two different densities. So the goal of this project was to observe how fluids with different densities can affect an object's buoyancy and how far down it sits in the fluid. Our goal is to further understand how the density of the fluid will affect the buoyant force that acts upward on the object. And through this, we'll be able to hopefully teach people about buoyancy in a much more visual and simplified fashion. And the main equation that we're going to be focusing on here today is the equation that governs the buoyant force that acts upon an object. So that's going to be right up here. FB, that's the buoyant force, equals negative rho times g times v. Buoyant force is equal to negative, which denotes that it acts opposite to the direction that gravity acts. So gravity pulls things downwards. Buoyant force will act upwards. Rho, that is the density of the fluid, not the object. G, that's just gravity, 9.81, and V is the volume displaced by the object, in the fluid. It is the volume displaced by the object in the fluid, not the volume of the object. These two are different things. So our experiment is going to consist of an object that we will be dunking into the fluids, a cage that keeps the object lined up vertically so it will be easier to measure, two different fluids of two different densities. So this time we have water and canola oil, and it's much better this way because water and canola oil do not mix. If you had two things that would mix homogeneously, this experiment might play out quite differently. And a vertical walled transparent container so we can take measurements nice and easy, and calipers and a scale so we can take data. So the setup, we used a 3D printer for this one. We printed out a 30mm by 30mm base by 56.4mm height hollow rectangular prism so we can drop ballast inside. In this case would be 3/4. And then we printed out a cage to be submerged in the fluid to ensure that our object would stay vertical and therefore have a predictable volume underwater that we can measure. So we added 2/4 to the object and we weighed how much it was, and later on we can see that it would be 50, no, not 50, it was 25.23 grams, I believe. So we take an object of this mass and we place it in a container. From there, we're going to fill it with fluid until the object can float, and then we're going to measure the height of the object that is above the water. Using that, we can subtract it from the known total height of the object to find the height that is underwater. We're going to repeat that with a second fluid. And then we're going to move on to the two fluid section. We're going to fill the container with two fluids. We're going to add the object, and we're going to repeat the height measurement. We do have to make sure that the object is intersecting both of the fluids in this case. Otherwise, it would simply be a one fluid measurement case. We also want to measure the height of the less dense fluid. So here's our predicted results. The oil layer we're going to set at 15 milliliters. The mass, 25.52 grams. This is the mass of the object. Volume, 30mm by 30mm. This is fixed. This is the base face of the object, so the amount that is underwater is not going to change. And then we have the height, which will change because as the object sinks down into a fluid of varying density, the amount that it sinks into it might not be the same, well, will not be the same for different fluids of different densities. Density of water, we're going to say, is 1,000 kilograms per cubic meter. And we looked up the specific density of canola oil, which was 0.912, so it would be 912 kilograms per cubic meter. In water, we have our buoyancy equation, and we have our F equals mg equation. This is gravitational effect on the cube, and this is the buoyant force of the water. So we have to do a force balance equation, mg equals rho gv. There should be a negative there. Actually, it's just force balance. Mg equals rho gv. So we have the mass of the cube in kilograms times the gravitational acceleration equals density of the water times gravity times base squared, that is 30 millimeters times 30 millimeters, times the height. And then if we solve for h, we get that the underwater section should be 28.35 millimeters down from the surface. And if we do the same thing for the oil, this time changing the density to 912, we find that the height should be 31.09 millimeters. So for the in-water and oil part, we still have our force balance equation. So the force of the cube stays the same, which would be gravitation, force, acceleration of gravity times the mass. But then since we have two fluids, we need to have two different forces for that. So we have the buoyant force of the oil and the buoyant force of the water. This is where the oil layer comes into play. So we have mg equals density of the oil times 9.81 times the base face times 15 millimeters. And this is fixed because the bottom face of the cube will be past the oil. So therefore, that entire section of oil will be displaced by the cube, and that is where the buoyant force comes from. So we have the base, and we have the height of the oil layer, which is 15 millimeters, plus the density of water times acceleration of gravity times base face times the height, which would be unknown. And this is not the overall height, this is just the height that's stuck down into the water. This is unknown because, well, we don't know how far down the cube's going to sink into the water. We know that it's past the oil, though, because, well, it has to be in this experiment. If it wasn't, then we'd just be back to square 2, I guess. So because the oil height is known, we can substitute that in for h while we solve for the depth that it goes down into the water. So if we solve for h, we get that from the absolute top of both fluids. So since we have oil sitting on top of water, we solve for h here. This is the h that is underwater. We get 0.0164 meters, so that's 14.67 millimeters. We add that to the thickness of the oil layer. We find our total height of the bottom face of the cube from the top of the oil layer to be 29.67 millimeters. These are our calculations, so if we move on to our recorded results, you can see that there's a bit of error, but it lines up fairly closely. Submerged height being 30 millimeters for water, submerged height being 34.1 millimeters for the oil, and submerged height of the combined fluids being 33.2 millimeters. And in these next few slides, we'll be able to show you exactly what we did in real life with these pretty little graphics and photos. So as we can see here, there's the object sitting in the water, and there's the cage. Otherwise, because if we didn't have the cage, this object would be sitting at a weird diagonal inside the water. So we printed this out to minimize the frictional force that it would impart onto the object so it would have enough clearance, but it would be able to keep it straight enough for measurements. And then here's the same thing for the oil. And here's the one for combined fluids. Alright. So, we have a bit of error between our experimental results and predicted results. So this could be due to human error. As I was measuring it, I might not have lined it up perfectly down to the millimeter, or it could have been assuming that the density of water was exactly 1,000 kilograms per cubic meter, because as temperature varies, the density of water also varies. Another error could have also come from the fact that we looked up the density of canola oil online rather than measuring it out for ourselves, and that seems to have been one of our larger sources, because on average our offset was about 2.73 millimeters, but it went higher when oil was present, as you can see in these two slides. We'll start from the top. Air in the water was 1.65 millimeters, air in pure oil was 3.01, and air combined was 3.53. The predicted results and data, however, do line up in the order in which we expect the height of the cube to be underwater. So we had water being the least underwater, oil being the most underwater, under oil rather, and then the combined to be sitting right about in the middle. So adjusted for error, we predict that the density of oil is actually around 872 kilograms per cubic meter. So through our experimental procedure, we're able to demonstrate the principles of buoyancy by looking at different fluids. We're able to experimentally demonstrate that the density of fluid is proportional to the volume displaced. We could clearly see that the box floated higher in the water than the oil. The test with the mixed solution was in the middle, as we would expect based on the buoyancy force equation. And I guess the reason why the height of the submerged height of the object under the water was less rather than the submerged height under the oil is because if we go to the buoyancy equation, we can see that the buoyant force is directly proportional to the density. So the higher the density, the higher the buoyant force. The higher the buoyant force, the less height submerged underwater. And hopefully with this presentation we can visualize and be able to kind of get fluid dynamics out to a few more people out there. All right, thank you.